Grundig W21351, Oscilloscope 1963. This is the documentation of the experience of a hobby project, available in video and in written form, made with the hope that it could be helpful to others. But any comment that could help me to improve my practice is also welcome and appreciated. This is a single-trace laboratory vacuum tube oscilloscope, built by Grundig in the 1960s. The unit arrived quite dirty and with some rust. There is also a visible damage on the bezel. The uniform layers of accumulated dust show also that the unit was never serviced. The power transformer responsible for the high voltage driving the CRT shows signs of excessive heating. There is an inventory plate on the back of the case, which tells the story of this item. It was formerly property of the Vocational School for Radio and Television Technology in Rendsburg, Germany. This drawing of the school building comes from the publication 75 Years of Vocational Schools in Rendsburg, 2004. Grundig made a few variants of the same oscilloscope model, with little changes in the schematics. For reference, this unit is type 51 and it has the serial number 2918. The correct schematic diagram for this unit has not been found, but the one from a previous version has been adapted, however with no component list. The few values that you can see here have been read from the components that have been inspected during the restoration. Before the restoration, the unit was still capable of showing some wobbly waveform. After removing the knobs, the bezel, and the front panel, I started replacing the selenium rectifiers with silicon diodes. Only for practical reasons, I restuffed the larger one. Then I looked for small electrolytic capacitors. Then I looked for paper capacitors. They were very good quality ones, but still paper. I was reluctant to deal with the filter capacitors, but I had to, because the B+ lines contained a significant ripple, which was, in fact, the cause for that wobbly behavior. Also, the special high-voltage filter capacitors had to be changed, because the original ones are paper caps, and the high-voltage transformer was already showing overheating problems, suggesting that they might have been deteriorated. Please notice that, for this oscilloscope model, the CRT is driven with about -2 kV compared to the chassis ground, which requires using filter capacitors rated for at least 3 kV. Due to the lack of space, and because of mounting problems, I had to plan a couple of boards to be connected together, one containing the high-voltage filter capacitors, and the other one for the B+ filter capacitors. You may see the board plans and the final result. Finally, the oscilloscope was able to operate properly, and here are all the parts that have been replaced. I decided to try to replace the broken bezel with a plastic ventilation flange having a compatible diameter. The base had to be cut to fit inside the original bezel frame. Some adhesive felt has been added to the base to push against the graticule glass. If I had a workshop with proper tools, I would shorten the new bezel, but that's okay. I like it also as it is. Also, the knobs needed some attention. The decorative cover of the larger knobs was missing, and all the knobs had a rather awful brownish color, very likely due to nicotine. I tried to clean them using detergents and solvents, including alcohol and even acetone. I also tried to brush them with some steel wool, but without success. I finally decided to paint the knobs. Then I used the decoration of other cheap knobs to cover the missing upper part. It does not look original, but it looks plausible together with the new long bezel, and I like it. This oscilloscope uses metric screws M3 and M4. In most cases, the original screws were rusty, and even treating them with a rust remover they appeared discolored. I replaced all the external screws and washers with shiny stainless steel crosshead equivalents. This oscilloscope was made for working at 110 or 220 volt AC only. However, nowadays it is more common to find slightly higher residential voltages. In particular, where this item will be used, the mains has a voltage of about 230 volt, possibly also reaching a value of 240 volt. During the restoration also the 3 selenium rectifiers have been replaced with silicon diodes, but without adding a resistor that would have reproduced the voltage differential of the original selenium technology. Under the circumstances, the oscilloscope would have to function with excessive voltages, and during the early tests it appeared that also the resistors R29 and R30 were becoming too hot. A resistor of about 80 ohm 50 watt has been inserted in series with the mains to drop about 30 volt with a current of about 400 milliamp. Considering that the added resistor reduces the initial current surge, the fuses have been reduced to 500 milliamp fast blow. The oscilloscope is working well with the reduced mains voltage. The in-circuit measured voltages are fairly close to the expected values. Only the tube heaters receive a slightly less voltage, but that does not seem to create any trouble. At the time of this restoration, a service manual for this oscilloscope was not available. The following adjustments have been deduced only by the information written on the schematic diagram. Astigmatism. While the focus can be always easily regulated from the front panel using the potentiometer R13, the astigmatism is an adjustment that is meant to be done rarely with the help of the trimmer resistor R10. Vertical operating point. The waveform that is rendered by the oscilloscope should usually appear in the middle, shifting its position with the help of the potentiometer R1, accessible from the front panel. However, it might happen that even turning this potentiometer from one end to the other, there is never a way to let the wave appear in the middle. If this is the case, it is necessary to adjust the general vertical position, setting what here is called vertical operating point. This is done with the help of the trimmer resistor R128. Calibration voltage. According to the schematics from the trimmer resistor R19, it is possible to set and get a sine wave of 0.4 volt RMS, which could be used to calibrate the vertical scale on the oscilloscope. During the restoration it was attempted to set the proper value of 0.4 volt RMS, but without success. It is possible that R20 and or R311 are out of value. But even if the correct voltage could be set, the signal comes out so distorted. This is due to today's appliances making all that noise in the power lines that it would be useless to rely on such a point of reference. Vertical calibration and symmetry. Instead of using the calibration signal to calibrate the vertical scale to the reticle that is printed on the plastic screen before the CRT, applying a sine wave signal from a reliable source generator, knowing what would be the expected height in centimeters, the trimmer resistor or 104 could be adjusted accordingly. The trimmer resistor or 117 could be then used to fix a possible asymmetry between the upper and the lower part of the wave that is represented. Horizontal operating point. Like for the vertical operating point, there is also the possibility to set the horizontal operating point if the potentiometer R7 is not in the condition to do its job correctly. For this, the trimmer resistor R5 can be used. Horizontal calibration. It is possible to calibrate the horizontal gain so that horizontally each centimeter on the CRT screen corresponds to the time selected. So, for example, selecting 1 millisecond per centimeter, each centimeter should contain the width of a cycle of 1 kilohertz. Similarly, selecting 1 microsecond per centimeter, a full cycle of 1 megahertz should be displayed on the width of 1 centimeter. The calibration could be obtained using a reliable function generator and adjusting the trimmer resistor R224. Capacitance compensation. If a square wave visualized with a selected vertical attenuation appears on the screen rounded or with an initial spike, it is probably necessary to adjust the trimmer capacitors C307, C310, C313, C315, and C317 to obtain a proper representation. You might have noticed that I put labels on the tubes with their identification code, using masking tape for that. This is okay, but if a tube becomes particularly hot, that label would slowly burn, becoming a dark piece of dirt attached to the glass. After the restoration was finished, I realized that I could have used high-temperature tape, writing on it with a permanent marker. This is what I will do in the next restoration project. The Grundig W2-1351 oscilloscope is ready. Internal calibration signal. As already mentioned, not very useful. Initially, the vertical resolution is set to the maximum 20 millivolt per centimeter. 50 Hertz, 50 millivolt peak to peak. (500 Hertz, 50 millivolt peak to peak). (5 kilohertz, 50 millivolt peak to peak). 50 kilohertz, 50 millivolt peak to peak. (500 kilohertz, 50 millivolt peak to peak). 1 megahertz, 50 millivolt peak to peak. The effective vertical resolution is now only about 30 millivolt per centimeter. (2 megahertz, 500 millivolt peak to peak). Signals above 1 megahertz suffer from a significant and progressive attenuation. 3 MHz, 500 mV peak to peak. 4 MHz, 500 mV peak to peak. 5 MHz, 2-volt peak to peak. 6 MHz, 4-volt peak to peak. 6 MHz, but with external sync. The following waveforms are generated at 100 kHz, 1 volt peak to peak, with a vertical resolution of 300 mV per centimeter. If you would like to contribute to this project, donating old electronics equipment or old radios in whatever condition they might be, provided that you do not feel any attachment, that could be helpful for my next restoration documentation and video production.